Let's talk about how the Vertex shader input relates to the input layout that we defined in the code. So the Vertex shader input can use all or a subset of the input layout elements in any order, as long as it refers to the semantic, the thing in uppercase, correctly. So currently we're using all three of those elements, and we are correctly referring to the semantic values, so that's okay. But this particular shader doesn't use the normal, so we actually could, and we will, delete that. I guess we're assuming that this input layout is used by some different shader program that does use normal, otherwise we'd get rid of it from there. But I just want to illustrate that an element can be present in the input layout without actually being used in a particular shader program. The other thing I said was they can appear in any order, so let's just move this colour to the top just to show that it's out of order. And I'll just run that so that you can see it does exactly the same thing. We haven't broken anything by doing that. But the semantic has to be correct, so if I spelled that wrong and tried to run, then that wouldn't work. I would have to make sure, I've got to make sure that these match, so the semantics match in both places. It doesn't really matter what the semantics are, as long as they match. So this should build and run again, now that I've got those uppercase strings, the semantics matching. So we're back to where we were before. Let's just change that back to the US spelling. So that's the input. The output, the relationship between the output, the Vertex shader output, and the pixel shader input uses different rules, actually different rules than the ones we've just talked about. The pixel shader input can use all or a subset of the fields in the Vertex shader output, but they have to be it has to be in order, and any fields that the pixel shader input ignores have to be at the end of the Vertex shader output. So let's see what we're doing. We've got position and colour, and we've got position and colour, so everything's obeying the rules at the moment. And we are using colour, but we're not using position. But like I said, I can't just delete that, because the ones that we don't use have to be at the end of the list. So I can first, before I delete that, I have to do some work and put that at the end. So let's go ahead and do that. How do we do that? Well, it's just a case of pushing that one to the end. I've got a little bit of work to do here because of the order in which I'm instantiating this output. So it's colour first, then position. That's right, colour first, then position. Come here, colour first, then position. That should still work exactly the same way. I've just refactored it, but the behaviour is exactly the same. Now I can delete position because I'm not using it. But I can't delete it from here, because position has to be there because the rasterizer needs it. So the transformed position that we're producing here has to go out to the rasterizer, even though the pixel shader doesn't use it. So yeah, so essentially what you do for your Vertex shader output is always make sure you've got your transformed position, and then optionally any other values that the pixel shader needs. Put those in there, put those at the top, and then go ahead and use them. So now let's play around and see what kind of thing you can do in these shaders. I thought we could play around with the colour. Let's just remind ourselves what it looks like. So it's got these colours that are coming from the vertices, but I thought we could just ignore those colours and just play around with something, see what we can do. So I'm just going to do it's not a very realistic kind of algorithm that I'll do, but at least it's something that'll demonstrate what we can do. So I'll make the colour a factor of position. So I'll just say output colour equals output input.position.x is, if it's less than 0, then we will make it red, and otherwise we'll make it blue. So I've done this, I'm actually grabbing the output's position, the x coordinate of the output's position, after doing the world transform, so that the actual colour will depend on the world transform, not on the view transform. So it won't matter which way the camera's looking or where the camera's located. The colour will be a factor of the actual geometry. So let's see what that looks like. Float 3. See what that looks like. So you see, it doesn't matter which way I look. This thing's red to the left of the x. It's red to the left of x, and it's blue to the right. So now, if I just move that after we've factored in the view, then now the colour will be a factor of what direction I'm looking at. So as I look over to the left, I'm actually, because the camera is essentially always looking down, at least in view space, the camera's always looking down the z-axis. So as I move, as I look around, that's affecting the view relative position of these coordinates of the positions, and so they're changing colour because I'm essentially moving them across the x equals 0 plane in view coordinates, but of course I wasn't doing that in world coordinates. See, now it's just relative to the actual geometry positions. So another thing, let's get rid of that. In fact, yeah. So let's do a similar thing in the pixel shader. And what I'm going to do though is I'm just going to bring that position back. Let's use that position this time. Actually, let me grab that. Save me typing it again. So input position. Now if I build this now, oh, I thought I was going to get I must have already changed this. Yeah, so previously I by default, when you add a pixel shader file and you set it to be a pixel shader, you get shader model 40 level 9.1 by default. So if you leave that at the default, then you'll get this error saying you can't read from position semantics. This is a system position semantic SV, system value position, which is different than that, but we can go into that some other time. So yeah, so you get this error by default if you try to read SV position. So looks like I'd already fixed that up when I went off camera. So I just changed it to 4, which is the minimum that will allow me to use that. So what I'm doing now is we're using the input position. This time we're using this in screen space, and in fact less than 0 isn't appropriate anymore. I want to be less than 800 because this is a 1600 wide resolution at the moment. So you can see now it's just completely, the colour is completely a factor of you know, the left hand up versus the right hand half of the screen. It's nothing to do with the geometry. It's not really to do with where I'm looking. It's really to do with where the pixels are being displayed on the screen. So that's the kind of thing you can do in the pixel shader. And another interesting thing we can do in the pixel shader is if I do a kind of little let me do a kind of checkerboard effect. If I add the X and the Y, So the X and the Y coordinates are in screen pixels. They are floats, of course. They're coming in here, so they're floats. So I'm just casting them to be ints and adding them together, and then doing a bitwise AND just to see whether the result is odd or even. If you add the coordinates together and figure out whether they're odd or even, that'll give you a checkerboard pattern. But this is just per pixel, so that's not going to look like a checkerboard pattern at the moment. It's going to be too small. It's going to look like a dithered pattern, so you won't really see what's going on. So I'm just going to divide the X and the Y by 16 just to kind of multiply. Essentially, that scales the whole thing up by 16. Let's make this a kind of grayscale. Let's run that, see what result we get. So you end up with this kind of, I mean, this is an unusual, this is not the kind of thing you usually see, but I just wanted to show you the kind of things that you can do with your pixel shader in just a tiny amount of code. Just shading that thing as a factor of the pixels, of the actual screen pixels that are being covered. And then the last thing I wanted to show is an alternative to using these input structures. Notice at the moment we've declared this input structure, and then we're accepting an instance of that into the main function. But instead, if we want, and this is entirely up to you, whatever you prefer, of course we can just accept those fields directly into the main function as flat parameters, and then just just tweak the code that consumes them a little bit. So that's equivalent to what we had before. And the rules are the same. You still use a subset or all of the input layout. Same rules. Doesn't matter what order they're in, but the semantics have to match. And then of course you can do the same with the pixel shader program. So we can just simplify this a little bit. Just need to tweak the code a tiny bit. And it should work the same way. Of course, we're not using that color anymore in that case. So we could simplify that. We could delete color from there and get rid of it. We'd have to fix this up, so in the interest of time I'll just let me just show you that we can get rid of position then, and put color.rgb back. So now we're back where we were. Yeah, let's get rid of that colour. I might as well just show you that. So we'll get rid of colour from there. Guess that's pretty simple to do. That should work. There you go. All right, well that's it for the introduction to pixel shaders and Vertex shader programs. We'll talk about transform and project a little bit more in the next video.